Hello, we're going to take a look at section 10.3 today, which is all about the ellipse and its uses. Our goals for today that we can find the key features of an ellipse, we can write the equation of an ellipse, and we can graph an ellipse. The definition of ellipse. An ellipse is the locus or the set of all points where the sum of the distances from two fixed points called foci is constant. Okay? So the distance from this focus to the point plus the distance from that point to the other focus is always the same, regardless of where we put that point around the ellipse. Some key features of the ellipse. Pardon me. The longer axis of symmetry, in this case it's this horizontal one, is called the major axis. So from here to here is the major axis. The shorter axis of symmetry is the minor axis. So from right here to right here is the minor axis. At each endpoint of the major axis, we have a vertex of the ellipse, so there are two vertices. Each endpoint of the minor axis is a co-vertex or a co-vertice, since there's two of them. And in the center, we have the center, and the foci, okay, are on the major axis. So, major property of an ellipse. What happens when we reflect an object off the side? And in fact, if we put an object at one focus and reflect it off the side of the ellipse, it will always reflect to the other focus. Doesn't matter where point we reflect it off of around the ellipse. Okay, if you start at one focus, it's going to reflect off the ellipse and go to the other focus. One way that gets used is with a medical device called a lithotripter, which literally means stone crusher. And what they do, if you have a kidney stone or a bladder stone, they do some imaging, x-rays, or ultrasound to determine precisely where that kidney stone is. And then they place the lithotripter so that the shockwave source is located exactly at the other focus of the ellipse. And so then when they turn on the shock waves, those waves will bounce off the sides of this elliptically shaped reflector and bounce so that they hit just the kidney stone, and it breaks it up into small pieces, which allows it to be passed in a much more comfortable way. The reason this is such a wonderful thing is that previously a tool that was used for bladder stones, kidney stones, was this device, which is called a lithotrite. And this device, or a similar device, was inserted through the urethra up until it reached in the bladder, and then the surgeon would grasp that bladder stone and crush it into pieces, and which would allow those pieces to be removed. Luckily, bladder stones, kidney stones are not as much of a problem nowadays as they were in older times. Our modern day diet has improved significantly, but it is still an issue for many people. And I don't know about you, but I would way rather have that device that uses the elliptically shaped reflector than to have this inserted inside of me. And yes, I can see even even through our computer screens that you are all squirming right now, right? Another use of the ellipse is a whispering gallery. There is one in the U.S. Capitol building. They designed the dome to have an elliptical ceiling. There's this urban legend that John Quincy Adams would pretend to be asleep at his desk, but what he was actually doing was listening to people in other parts of the room. If he was located at one focus in the room and they were located at the other focus of the room. Unfortunately, the acoustic properties of the building are not as pronounced now because it's been renovated, but it's still an interesting note. And there are other places in the world that have whispering galleries that function more completely. Another note, most of our planets actually orbit in elliptically shaped orbits around the sun. This is, you can tell a little bit of an old diagram because it does still show that Pluto is the 9th planet, which is a little bit out of date at this point. Ships and cars also use ellipses. In fact, The hulls of ships and submarines are designed to have an elliptical cross-section, which minimizes resistance and increases the buoyant force. In an internal combustion engine, they design the piston and cylinder to have an elliptical cross-section to improve the flow of oil and reduce friction and increase engine life. All right, some variables that we need to know when we're working with the ellipse. A is the distance from the center to the vertex, or in effect, the length of the semi-major axis. B is defined as the distance from the center to the covertex, or the length of the semi-minor axis. Remember, semi is halfway across in that direction. And C is the distance from the center to the focus. And bearing those in mind, actually, let me back up a second. There is a little equation that shows the relationship between those three variables, that b squared plus c squared is equal to a squared. Okay, looks a little bit like the Pythagorean theorem, but keep in mind that these values of a, b, and c are referring to specific segments within the ellipse. All right, the standard equation of an ellipse. Let me back up. For a horizontal ellipse with a center at the coordinates h, k, we have x minus h quantity squared over a squared plus y minus k quantity squared over b squared is equal to 1. For a vertical ellipse, we have the quantity x minus h squared over b squared plus the quantity y minus k squared over a squared is equal to 1. You might pause for a moment here and look at what is the difference between these two equations. How could you tell by looking at an equation whether one is horizontal or vertical? Remember that A is the distance from the center to the vertex, which is always going to be a longer length than from the center to the covertex. So it is going to be a horizontal ellipse if the number under your x squared term is the larger number, and it'll be vertical if the number under the y squared term is the larger number once it's in standard form. All right. First example, we're going to find the standard form of the equation of an ellipse with a focus at with foci at 2, -1 and 2, -7, and a major axis of length 10. Many of you will find it helpful to sketch a graph to help you find your vertex and identify your values of A, B, and C. So we have one focus at the point 2, -1, another focus at the point 2, -7. Your vertex has to be exactly in the middle of those, or sorry, not your vertex, your center has to be in the middle of those. And I apologize, that's a little typo there. That should be saying you find the center and the values of A, B, and C. So the point that's in the middle of 2, -1 and 2, -7 would be 2, -4. So there's our center C. It tells us that our major axis has a length of 10. So we know all the way across in this direction is a length of 10. So we can kind of sketch in what we think this is going to look like. And so since the major axis has a length of 10, A, the semi-major axis from the middle to the edge would have to be 5. We know that C, the distance from the center to the foci would be 3 spaces. And in order to find B, we're going to have to use that equation B squared plus C squared is equal to A squared. So if we substitute 3 in for the C and 5 in for the A, we can do a little bit of algebra. 3 squared is 9, 5 squared is 25. To get B squared by itself, if we subtract 9, B squared would equal 16, which means B is equal to 4. And now knowing our values for A, B, and our center, we can write our equation. This is a vertical ellipse. So if we put B in here, B squared, 4 squared is going to give us 16. A is 5, so 5 squared gives us 25 in the second denominator. Since our center is at 2, -4, we're going to have x minus 2, and when we subtract the -4, we're going to get a plus 4. So our final equation, the quantity x minus 2 squared over 16 plus the quantity y plus 4 squared over 25 is equal to 1. Example 2, we're going to identify all features of the ellipse and then sketch the graph. For the equation, the quantity x plus 2 squared over 16 plus the quantity y minus 3 squared over 9 is equal to 1. We know that this is a horizontal ellipse. We have a larger number underneath the x squared term in this equation. We know our center is at -2, 3, basically the opposite of each of the numbers inside the parentheses. We know in a horizontal ellipse, a squared is the number underneath our x squared term. So if a squared is 16, a would have to equal 4. B squared is underneath the y term in a horizontal ellipse equation. So if b squared is 9, b would have to equal 3. In order to find our foci, we're going to have to use the equation b squared plus c squared is equal to a squared. So if we substitute 4 in for a and 3 in for b, 3 squared is 9, 4 squared is 16. If I subtract 9 from both sides, c squared is equal to 7. Thanks, neighbors, if you can hear all the background noise. And if we finish solving, taking our square root, c would equal the square root of 7. All right, so we already knew our center was at -2, 3. Our vertices, okay, because our semi-major axis is 4, we know we're going 4 spaces to the left and right of our center to get to our vertices. So 4 spaces to the left of -2, 3 would be -6, 3. 4 spaces to the right of the center would be +2, 3. For our co-vertices, since our semi-minor axis is 3, we'd be going 3 spaces above and below our center to find those co-vertices. So 3 spaces above -2, 3 would be the point -2, 6. 3 spaces below -2, 3 would be the point -2, 0. And feel free to sketch this out on a graph so you can count the number of spaces. And then our foci, since this is a horizontal ellipse, the foci are going to be to the left and the right of the center. So square root 7 spaces to the right of the center would be -2 plus square root 7, comma 3. Square root 7 spaces to the left of the center would be -2 minus square root 7, comma 3. Or if you want, you can actually write that as just -2 plus and minus square root 7 over 3. If you're doing your assignment on WebAssign, you might have to write them out as 2 separate points, but otherwise you can just combine it into one like this using the plus and minus symbol. And now if we want to make our graph, plot your center, plot your vertices, plot your co-vertices, and then you really can just connect them with a elliptical shape, and then make sure you plot your foci on there as well. Since square root of 7 is a little bit in between 2 and 3, since square root of 4 is 2, square root of 9 is 3, so square root of 7 is in between those. Go a little bit in between 2 and 3 spaces on either side of your center to approximate where those would be on your graph. All right, and I believe this is our last example for today, example 3. We're going to write the equation of the ellipse in standard form, identify the center, vertices, co-vertices, and foci. And our equation that we're going to be working with is 9x squared plus 4y squared minus 54x minus 8y plus 49 is equal to 0. All right, first thing I'm going to do is I'm going to group both of the x terms in one set of parentheses and both of the y terms in a second set of parentheses. So in my first set, we have the 9x squared minus 54x. In my second set of parentheses, the 4y squared minus 8y, and then kick that 49 outside of the parentheses, okay, is equal to 0. With an ellipse, to get it into standard form, we actually get to use completing the square twice. I know you're all so happy right now, right? In order to complete the square, though, we do need to factor out any coefficient that's in front of our square term. So in our first set of parentheses, we're going to factor out the 9. In our second set of parentheses, we're going to factor out the 4. So if I factor out 9 from the x's, I'm going to have 9 times parentheses x squared minus 6x. Factor out the 4 from the y terms, we get 4 times the quantity y squared minus 2y. The 49 is still outside of the parentheses, is equal to 0. And now we're going to complete the square with each set of parentheses. And remember, with completing the square, we're going to take our b value, so the number in front of your linear terms, in front of the x term here, in front of the y term here. You're going to divide it by 2 and then square it, and that'll be what you add inside the parentheses. So negative 6 divided by 2 is negative 3. Negative 3 squared is positive 9. That's what I'm adding inside this first set of parentheses. Now to balance out that positive 9, I didn't just add 9. I added 9 times 9, 81. So I need to subtract 81 outside of the parentheses to balance that. For our second set of parentheses, negative 2 divided by 2 is negative 1. Negative 1 squared is positive 1, so that's what I added inside the parentheses. And to balance that out, we didn't just add 1, we added 4 times 1, so we're subtracting 4 on the outside of the parentheses. Now if we do a little bit of simplifying, half of negative 6 is negative 3, so we're going to get x minus 3 squared. Half of negative 2 is negative 1, so we get y minus 1 squared. We still have the 9 and the 4 out in front. And then 49 minus 81 minus 4 gives us a minus 36. Now to get it into standard form, we need to get one side equal to 1. To make that happen, our next step would be to add 36 to both sides. So now we have 9 times the quantity x minus 3 squared plus 4 times the quantity y minus 1 squared is equal to 36. And then to get this side to equal 36 and get our fractions on this side, we're going to divide everything in this equation by 36. Okay. 9 goes into 36 4 times. So we're going to get x minus 3 squared over 4 plus 4 goes into 36 9 times. So y minus 1 squared over 9 equals 36 over 36 is 1. And now that it's in standard form, we can identify all of our key features. We know that this is a vertical ellipse because the number under our y squared term here is the larger number. We know our center is going to be at positive 3, positive 1, looking at what's inside each set of parentheses there. We know that a is 3, right? A squared here is 9, so a has to be 3. Our semi-minor axis b, well, 4 is the same as 2 squared, so b has to equal 2. In order to find our foci, we're going to use that equation, b squared plus c squared is equal to a squared. So if we put 2 in for b, put 3 in for a, or hey, you might even notice that hey, these equations have the b squared and the a squared, so if you want to just substitute 4 in for b squared and 9 in for a squared, you could also do that. And get this. If we subtract 4 from both sides, c squared is equal to 5, which means c is equal to the square root of 5. Since this is a... All right, so for our vertices, our semi-major axis A is 3. Since this is vertical, that's going to be 3 spaces above and below our center. So 3 spaces above the point 31 is going to be 3, 4. 3 spaces below our center takes us to 3, negative 2. Our co-vertices, because B is 2, we know the co-vertices are going to be 2 spaces to the left and right of our center. So 3 spaces to the left of 3, 1. I apologize, I have a typo here. That should actually be 1, 1 and 5, 1. Easy to make a mistake. Make sure you're looking at your center and not your vertices. And then for your foci, since this is a vertical ellipse, it's going to be above and below your center. So 3, 1 plus and minus square root 5. If you're doing it on web assignment, you have to write it out separately. You have 3, 1 plus square root 5, and then 3, 1 minus square root 5. And your assignment, if you're on WebAssign, it's the 10.3 2020 assignment. Or if you're doing it out of your book, 10.3 Page 714, numbers 5 through 8, 22, 23, 29, 36, 40, and 45. I hope these examples help you with your assignment. Please reach out if you have any questions. Good luck!